In this series of videos, you will learn how to solve different types of numerical examples on singly reinforced section using working stress method and limit state method. So welcome to lecture series on design of RCC structures. I have categorized the numerical examples on singly reinforced beam in 4 categories. That is, first, to calculate moment of resistance of singly reinforced section, then to calculate safe load carrying capacity of the section, to calculate actual stresses in concrete and steel, and to design the beam. So there are two types of problems mainly, that is analysis type problem and design type problem. The first three types, that is to calculate moment of resistance, self load carrying capacity and actual stresses, these problems are analysis type problem, and fourth one is design type problem. What is main difference in analysis type problem and design type problem? It is that in analysis type problem we know the dimensions of beam section, already we know the section size, whereas in design type of problem we have to decide the beam section. Now in this video, we will learn how to solve a numerical example to calculate actual stresses in concrete and steel using working stress method. So here we are going to study how to calculate actual stresses in concrete and steel in singly reinforced section using working stress method. So for this, first of all, let us see what are the different steps involved in calculating the stresses in concrete and steel. So here, as I told you that the dimensions of the beam is given. Dimensions means width of the beam and depth of the beam will be known, and also the expected loading or bending moment will also be given. So we are interested in calculating actual stresses in concrete and steel, actual stresses in extreme fiber, because you know that stresses are maximum at the extreme fiber. So what are the different steps? Step number 1 is, if the load is given, first of all you have to calculate the bending moment from the different support condition if the support condition is given. Otherwise sometimes bending moment is directly given, but if it is not given and load and span is given, then you can calculate bending moment using standard formula. For example, in simply supported beam, maximum bending moment is WL square by 8, or for cantilever beam the maximum bending moment is WL square by 2, like that. After calculating bending moment, then you have to decide the position of actual neutral axis. After that, we calculate the permissible stresses in steel. So we are calculating permissible stresses in steel and concrete. So first of all, we calculate permissible stresses in steel by equating bending moment to moment of resistance from tension side. I will explain these steps while solving the problem. And then afterward, the last step, after calculating the stress in steel, we calculate stress in concrete by equating bending moment to moment of resistance from compression side. There is one more method to calculate the stress in concrete, that also we will discuss by using similarity of triangle. So let us solve a numerical example using working stress method. So let us consider this example. So we are interested in calculating the actual stresses developed in concrete and steel for a singly reinforced section, 300 millimeter width, and effective depth is 500 millimeter. Effective depth means it is measured from the top fiber to the center of reinforcement. Okay, up to that it is 500 millimeter. Then span of the beam is given and loading is given. There are 4 bars of 20 millimeter phi and M modular ratio is 90. So this is the given data. Required is actual stresses. Width of the beam is 300 millimeter. Effective depth is 500 millimeter. Beam is simply supported. That means we have to calculate bending moment WL square by 8. Then it is subjected to uniformly distributed load of 12 kilonewton per meter. Now in this case the load is given. Sometimes load may not be given. Then in that case you have to calculate the slab depth will be given. Then in that case you have to calculate the load on the beam. Now this load also includes the self-weight. But if it is excluding self-weight, then you have to add the self-weight to that UDL. Then beam is reinforced with 4 bars of 20 millimeter diameter. And modular ratio is 19 in this case. Now this is the given data for which we want to calculate the stresses. Just now we have seen what are the different steps involved in design of this, in calculation of actual stresses in the beam. Now let us understand how to solve this numerical example. So given data is the span of the beam is 6 meter, the width of the beam is 300 millimeter and effective depth means up to the center of the reinforcement 500 millimeter. There are 4 bars given in the problem and span of the beam is 6 meter. Again we want to calculate what is the stresses developed at the extreme fiber, means where extreme fiber for concrete for compression is this. At this level what is the stress developed? Similarly at this level, that is at the level of steel, means here. So at these two locations what are the stresses developed in the beam? This is the problem. Now data given is span 6 meter and uniformly distributed load 12 kilonewton per meter. Now first step is to calculate maximum bending moment. Now how we will calculate the bending moment? Since it is simply supported beam, you know that bending moment is WL square by 8. If you calculate you will get 54 kilonewton meter. After calculating bending moment, next step is to calculate actual neutral axis. So we have to locate this neutral axis. How we will locate this neutral axis? By taking the moment of areas about neutral axis. Now this neutral axis divide this beam into two areas. First is this concrete area, and you must be knowing that in RCC beam we neglect the concrete in tension zone. That means we assume that this much concrete is only available to resist the bending moment and this steel is available. There is no concrete below this line which is in tension zone. So we assume that since it is simply supported beam, top portion will be subjected to compression and bottom portion will be subjected to tension. So we neglect concrete in tension zone and therefore we consider only this green portion while taking the moment about neutral axis, and then by taking the moment of this area of steel about the neutral axis we have to consider equivalent concrete area. Because this is different type of material, concrete and steel is not a same material, therefore first of all we have to calculate equivalent area of this steel. Now what is equivalent area? That you must have learned in your strength of material. So this steel is converted into concrete area, that is called as equivalent concrete area. Now this is width and this is the effective depth. XA means the actual neutral axis depth from the top compression fiber. Now this area, steel area, we have to convert into equivalent concrete area. So what is equivalent concrete area and how it is calculated? It is converted to concrete, which is equal to M into AST. If AST is the area of bars, then equivalent concrete area is we get from by multiplying it by M. So we have to take moment of this top area about neutral axis and this bottom area about neutral axis. Now what is moment? Moment means this area multiplied by distance from the CG. So let us calculate it. M is given 19 and there are 4 bars of 20 millimeter, 5 bars. So if you calculate what is total area, you will get 1256.64 millimeter square. Now we have to take moment of equivalent area means M into AST, not moment of AST. We have to take M into AST. So let us see how to take this moment. Now for top portion, what is area? Area is B into XA, where it will act at XA by 2 from the neutral axis. So what is the moment? Area is B into XA multiplied by XA by 2. So it is BXA square by 2. So on the left side, you can see BXA square by 2. Then on right side, we take moment of equivalent area. What is area? Area is M into AST. And what is its distance from neutral axis? It is D minus, total is D minus XA. So using this formula, we calculate XA. So substitute everything. You will get quadratic equation here. Calculate XA, solve this equation. You will get value of XA which is 213.54 millimeter. So this is the second step to calculate actual neutral axis. How we calculate it? By taking moment of areas, area of concrete and equivalent area of steel about the neutral axis. Then next step is to calculate the stress. So the aim of the problem is to calculate the stresses only. So we are going to first calculate the stress in steel, that is sigma st. How we calculate it? We calculate it by equating bending moment to moment of resistance. Now let us see what is meant by moment of resistance. So we will draw the stress diagram. You know that the stresses are maximum in concrete at the top. It is like this, and this is what we want to calculate. And you know that towards neutral axis the stresses reduces, because at neutral axis there is no stress, stress is 0. So this is triangular variation in working stress method. So this is the stress diagram for concrete. At the level of steel, since we are neglecting concrete area, there will not be any triangle below this neutral axis. Okay. So this distance is XA from top. So compressive force is developed in the top portion, which is denoted by capital C. Similarly, this C where it will act? It will act at the CG of this triangle stress diagram. And what is the CG of triangle? It is XA by 3. Then stress in steel will develop at the level of steel only. It will not be a triangular variation, because here the steel is concentrated at one level only. So tension is developed here at the level of steel. Now distance between this total compression and total tension is called as lever arm. So this is the distance and it is denoted by Z. Lever arm is denoted by Z. How much is Z? Total distance is D. Here it is given D minus XA by 3. So lever arm is D minus XA by 3. Now we are equating bending moment to moment of resistance. Bending moment we have already calculated. and moment of resistance. Now we will see how to calculate. Since we are calculating sigma st, we have to take moment of resistance from tension side. What is moment of resistance? It is nothing but moment of couple. What is moment of couple? Moment of couple means the force multiplied by lever arm. Any one force, either C or T, multiplied by lever arm. So we are calculating from tension side, so we will take T into Z. So here we will equate bending moment to moment of resistance, and moment of resistance is nothing but T into Z. Now you know that T is nothing but a force, tensile force developed in steel. You know that stress is equal to force upon area, or force is equal to stress into area. Now T is a force which we can replace by stress into area. Z we know how to calculate. Now how we will calculate T? By multiplying stress into area. So bending moment we have already calculated, WL square by 8, 54 into 10 raised to power 6. T is stress into area. Now area is AST and stress is sigma ST. And Z we know D minus XA by 3. So this is nothing but T, AST into sigma ST, and this is Z. So we will multiply this and equate it to bending moment. Now what is the unknown quantity in this? Unknown quantity is only sigma ST. So from this expression we can calculate the value of sigma ST by equating this equation. So if you solve this equation, you will get sigma ST is equal to 100.209 Newton per millimeter square. So this is how we get the value of stress, actual stress developed in this tensile reinforcement. Now we will see how to calculate the stress in concrete. Now stress in concrete is denoted by sigma CBC. Sigma CBC means sigma is stress, C means concrete, B means bending, and again C means compression. Stress in concrete in bending compression. How it is calculated? Now it is calculated from compression side. Similarly, we equate bending moment to moment of resistance. Now bending moment we have already calculated, and moment of resistance is nothing but moment of this force C into Z. Now C is again force which is equal to stress into area. So force is stress into area. Now what is stress here? It is not constant. Stress is varying. Therefore we have to take average stress. At the top it is sigma CBC. At neutral axis it is 0. So average stress is sigma CBC plus 0 divided by 2. So it is half sigma CBC. So we get, if you substitute bending moment we have already calculated. C is what? It is area into stress. Area means this B into XA. This is green color, shown by green color. B into XA is the area which resists compression, and stress is average stress in this stress diagram, that is sigma CBC by 2, and lever arm is D minus XA. So this is nothing but the force C, and this is the lever arm. Okay, now in this only unknown is sigma CBC. So we calculate sigma CBC using this expression. If you solve this expression, you will get sigma CBC as 3.93 Newton per millimeter square. We can calculate this sigma CBC using one more method. So we will discuss the alternate method to calculate sigma CBC. First we have seen how to calculate sigma CBC by equating bending moment to moment of resistance. Now second method to calculate sigma CBC is considering similarity of triangle. Now here this is the alternate way to calculate sigma CBC. You can use any one way, whichever you find more easier, that you can use. So here we draw the stress diagram. This is called as equivalent stress diagram because we are considering here equivalent concrete area. So here XA, this is sigma CBC. So here at bottom we are considering equivalent stress, which is denoted by sigma ST by M. So if you apply similarity of triangle to this and write down the equation, you will get sigma CBC upon sigma ST by M is equal to XA divided by D minus XA. XA value we have already calculated, D we know, sigma ST we have calculated, M is also known. So from this expression we can calculate sigma CBC. So you can use any method to calculate sigma CBC. So if you substitute everything here, you will get same value of sigma CBC, that is 3.93 Newton per millimeter square. So finally, our final answers are sigma CBC is 3.93 Newton per millimeter square and sigma ST is 100.209 Newton per millimeter. So I hope now you must be able to calculate the actual stresses in singly reinforced beam using working stress method. So thank you. Stay connected to watch next video. Thank you very much.